In pharmaceutical development, before a newly synthesized drug can advance a single step, you have to prove its exact molecular structure. The most powerful analytical tool available for this task is nuclear magnetic resonance spectroscopy, or NMR. This diagram illustrates the two primary methods. On the left, Proton, or 1H NMR, highlights the hydrogen atoms. On the right, carbon-13 maps the carbon backbone. But you face two constraints. NMR machine time is highly expensive, and you only have milligrams of sample. Selecting the right scan involves balancing your available machine time against the specific structural data you need to extract from a sample. Both techniques operate on the exact same principles of quantum mechanics. When you place NMR active nuclei inside an external magnetic field, their spins align, creating discrete energy levels. Hit those aligned nuclei with specific radio frequencies, and they absorb the energy, flip their spin, and release a detectable signal as they relax back to normal. They even use the same baseline reference standard, tetramethylsilane, anchored right at 0 parts per million. Because they rely on the exact same underlying physics, their massive differences in practical lab utility stem entirely from the natural properties of the specific nucleus you choose to target. This comparison matrix tracks the first major parameter, natural abundance. Almost all naturally occurring hydrogen is NMR active. A proton scan catches this abundance, producing massive signal strength almost instantaneously. Carbon is vastly different. Nearly 99% of it exists as carbon-12, which is completely NMR inactive. To the sensor, the vast majority of your molecule is invisible. Carbon-13 also possesses an intrinsically weaker magnetogyric ratio. Combined with its low abundance, its overall sensitivity drops to roughly 5,700 times lower than a proton scan. To compensate for that weakness, a spectrometer has to run hundreds or even thousands of consecutive carbon scans and average them together just to distinguish the real signals from the baseline background noise. A proton scan delivers answers from microscopic samples in a few minutes. A carbon scan demands more physical sample and monopolizes machine time for hours or even days. The second parameter on our matrix is the clarity of the resulting spectrum, starting with the chemical shift range. The narrow 0 to 12 ppm window of proton NMR frequently causes signals in complex drug molecules to bunch up and overlap, muddying the data. Carbon spans a much wider range, from 0 to 220 ppm. This spreads signals out so widely that signal overlap is almost entirely eliminated. This wide spacing lets you immediately identify specific structural anchors. Carbonyls isolate clearly between 190 and 220, and aromatics group nicely between 110 and 160. We also have to account for signal multiplicity. Proton spectra feature complex multiplet patterns because neighboring hydrogens interact and split each other's signals. Standard carbon NMR uses a technique called broadband decoupling. This intentionally erases all hydrogen-carbon coupling, leaving only clean, single peaks known as singlets. Proton NMR forces you to untangle crowded, complex splitting patterns to infer structure. Standard carbon NMR trades away that proximity data to deliver an absolutely clear, unambiguous map of the carbon backbone. Our final matrix parameter is integration, and the ability to quantify molecules mathematically. The area integrated under a proton peak is directly, perfectly proportional to the number of hydrogens creating that signal. This mathematical certainty allows you to determine exact mixture ratios and verify purity immediately, without needing to build a calibration curve. Carbon NMR lacks this direct proportionality. Signal intensities are altered unpredictably by varying relaxation times and a phenomenon called the nuclear Overhauser effect. You can force a carbon scan to become quantitative, but it requires extreme, impractical time delays between scans to allow every single carbon atom to fully reset. Proton NMR operates as a rapid mathematical instrument for determining exact purity. Carbon NMR operates strictly as a qualitative mapping device. This decision flowchart translates these trade-offs into practical lab application, starting with one question: what is your primary analytical goal? If your task is monitoring drug stability, conducting routine purity checks, or determining the ratio of components in a formulation, you take path A, straight to Proton NMR. If you need to identify quaternary carbons, carbons with no attached hydrogens that are invisible to a proton scan, or differentiate complex structural isomers, you take path B, committing to carbon NMR. Your choice is dictated entirely by whether your priority is speed and math or structural completeness and clarity. Path C covers the workflow for elucidating the structure of a completely novel active pharmaceutical ingredient. For completely novel molecules, these techniques form a sequential pipeline. You start with Proton NMR as a rapid scout to confirm baseline functional groups and purity. With that baseline secured, you run a carbon scan overnight as the heavy artillery to map out the hidden structural skeleton and quaternary branch points. You then layer advanced 2D techniques, like DEPT and HSQC on top, to bridge the hydrogen and carbon data into a single comprehensive model. Math